It is common to come across so-called survival analyses in epidemiology. We're going to look at a few methods for survival analysis, with the caveat that this is quite a deep topic, something that you could learn a lot more about. To start with, we're going to look at what is known as the Kaplan-Meier method, or the Kaplan-Meier estimates, which is quite common to come across. Okay, let's look at this example here in this table. This is data for a cohort that we've followed of 1,000 people. Well, they started off as 1,000 people. And we've got them data for them from time 0, 1, 2, and 3. Let's start with time 1 here. At time 1, 5 people transitioned in the cohort. And the transition in this case could be from life to death, or it could be from a non-disease state to a disease state, for instance. Not having cardiovascular disease to having cardiovascular disease, and so on. There were 0 people censored, so we have data for all our people in the cohort at time 1. There were 1,000 people at risk, which basically means that we started off with 1,000 people in the cohort. Nobody transitioned at time 0, so everybody's still in the cohort at time 1. So there was still 1,000 people that were at risk. Because the 5 people transitioned at time 1, we had the transitions over here. We got 5 out of 1,000 that transitioned, and so the probability of transitioning at time 1 is 0.5%. Then the probability of not transitioning is 100% minus those 0.5%, giving us 99.5%. And then the probability of not transitioning from time 0 up until time 1, well, that's basically asking, what's the probability that I make it through time 1? Well, to do that, you have to make it through time 0. Everybody did that, so that's 100% here. You multiply that with the probability of making it through time 1, which was 99.5%. And so the probability of surviving up and through time 1 is 99.5%. Okay, let's move on. Time 2. At time 2, we had 4 people transitioning in our cohort. There were 2 people that were censored. Basically, that means that we've lost them, and we can't contact them, we don't have follow-up data on them, so we don't know anything about them. They're lost to follow-up or missing data. Okay, how many are at risk at time 2? Well, we started out with a cohort of 1,000 people, but in time 1, 5 individuals transitioned. And so we can remove them because they're no longer at risk. They're in the risk group, so to speak. They've had the disease. They've transitioned already. So those 5 we could remove, and also the 2 that were censored, leaving us with 993 individuals at risk at time 2. We then calculate the probability of transitioning at time 2 by taking the number of transitions, 4, and dividing by the individuals at risk, 993, giving us 0.4%. So this is kind of crucial to understand that the probability of transitioning that we're calculating here is based on you making it this far. So I'm saying that the probability that you're going to transition at time 2 is 0.4%. But that sort of includes the idea that you have to make it to time 2. So the probability of transitioning given that you made it to time 2. This is what is often referred to as a conditional probability. It's a probability that applies conditioned on that you made it this far. We can calculate the probability of not transitioning, so that's 100% minus 0.4%, giving us 99.6%. And then we can also calculate the probability of you making it this far, so making it through cycle 2. To make it through cycle 2, you have to make it through cycle 1. That's 99.5%. We had that in the previous row. And then you multiply that with the probability of making it through cycle 2. That's 99.6%, giving us 99.1% probability. And we continue on row 3. We have 3 transitions, 1 censored. We have 993 people still in our cohort. We reduced by the 4 people that transitioned in the previous time cycle. We remove the 1 individual censored, gives us 988 at risk. We take the 3 transitions and divide with the people at risk, giving us 0.3%. That's the probability that you're going to transition given that you made it to time 3. We calculate the probability of not transitioning, and we calculate the probability of making it through cycle 3. This last column here represents what we call the Kaplan-Meier estimate. It's an estimate of the probability that you survive from time 0 to time 1. So you see, you could actually plot these survivals, 100%, 99.5%, 99.1%, 98.8%. So you could plot them. And these are popular to plot because you get these Kaplan-Meier curves, or survival curves, as we've sort of called them before. And you could visualize them. And you could calculate them for different cohorts who have been exposed differently, perhaps smokers versus non-smokers, or somebody that takes a medication versus somebody that doesn't take a medication, somebody that's had surgery compared to people who didn't have the surgery. And you could look at how these survival curves differ. There are statistical tests that you can use to see if these are statistically significantly different, called a log rank test. You do that with caution. I'm just telling you, be careful. And it's a neat way of getting a basic understanding of the data. It has some problems because you can't adjust for any confounders. There's no way of you saying that you want to adjust for instance, age and gender and so on. Well, there are ways, but it becomes very complicated. And so if you want to take this a step further, you want to look at something known as Cox proportional hazard regression, or other types of hazard regressions. And we're going to look at those. To get to Cox proportional hazard regression, we're going to first have to define the hazard rate and the hazard ratio. The hazard rate can be thought of as the probability of transitioning at time t given that you made it to time t. We've actually already seen it in the example above with the Kaplan-Meier. We're just going to look at it again here. And then the hazard ratio is a contrast between two hazard rates. Just like the odds ratio is a contrast between two odds, the hazard ratio is a contrast between two hazard rates. Now we're going to have the blue cohort here and the orange yellowish cohort here. We have data on different cycles in time, so it could be years or minutes, but time 0, 1, 2, and 3. We have the number of people transitioning, the number of people censored, the number of people at risk, and we get the probability of transfer, that is the hazard rate. This is what we call the hazard rate. It is the probability that you will transfer from the non-disease state to the disease state, given that you made it this far. So it's exactly as when I showed the Kaplan-Meier. So you could look at the Kaplan-Meier material to see how to exactly calculate this. But it's just basically the number of people transitioning at a given point in time divided by the number of people that are still at risk at that point in time. And then here in this cohort, exactly the same. I've just changed the numbers a bit so that the cohort's a little bit different. So in this cohort, we had 5 people transitioning at time 1, and in the yellow cohort, we had 3 people. And a few other numbers are different here as well. So we've got hazard rates here in the last column in each table. These are the hazard rates. But what is the hazard ratio then? At time 1 here, we have 0.5% hazard rate in the blue cohort divided by 0.3% hazard rate in the yellow cohort, which gives us 1.67. So 0.5 divided by 0.3 gives us 1.67, and that is the hazard ratio at time t equals 1. The same calculation at time t equals 2 gives us a hazard ratio of 2.0, and at time 3, the hazard ratio is 0.75. So what we can say is that the blue cohort is experiencing events at higher rates at time 1 and 2, but at a slower rate at time 3. So it's a comparison or a contrast between two hazard rates. And it tells us, if we want to think about it more abstractly, what's the relative speed between these two cohorts, in a sense, that they are experiencing these events. And if you have a higher hazard ratio, then one group is experiencing this a lot quicker. And if the hazard ratio is 1, then both groups are experiencing it equally. And obviously, if it's lower than 1, just like an odds ratio, then the other group is experiencing it at a higher rate. Okay, so the hazard rate is something that is defined based on one cohort here, and the hazard ratio is a contrast between those two. If you're not used to reading regression equations, then don't freak out. We're just going to look at this equation and break it down. You don't really have to understand what's going on, but it will give you an idea of what this Cox proportional hazard regression is trying to do. Now, what we're going to say is, what if we could assume that the hazard ratio is almost constant over time? So in our previous examples, we saw that the hazard ratio actually was a bit different for every point in time between the blue cohort and the yellow cohort. But what if we could assume that, well, the hazard ratio is more or less constant over time? Then we could do Cox proportional hazard regression, which would also allow us to actually adjust for confounders such as age and gender and so on. So that would be the benefit of doing this above the Kaplan-Meier method. So just breaking down the basic structure of the regression model, what we're trying to calculate, this HT, is the probability of transitioning at time t given that you made it to t. And that is what we've just said before, is the hazard rate at time t. You're asking yourself, I've made it to cycle 2. What is now the probability that I will transition in this cycle? Okay, that's what we want to get to. That is our left-hand side of the equation. On our right-hand side, we say, well, there's this H0t, and that's the baseline hazard. Everybody has this. So this is something that represents the overall hazard of this event happening. So we all have a baseline risk of cardiovascular disease. Well, this is the baseline hazard for cardiovascular disease at this point in time. So this is something that is common for everybody in our cohort, or actually in our population really, because then we might have different cohorts. One cohort that has been exposed to some treatment or surgery, and another cohort who has not been exposed. And that is represented by the second part. The second part just tells us by how much we should multiply this baseline hazard given that you have been exposed. So everybody gets this part, but only those who have been exposed get this part of the equation. So this is the part of the equation that represents how much we should multiply the baseline hazard if you've been exposed, and this is then the hazard ratio, right? So we're saying by which magnitude should the hazard increase given that I have been exposed. And this you could enter into any statistical program, and it will give you the number exponential b1. And if exponential b1 is 2.0, then the hazard ratio is 2.0 when comparing the unexposed to the exposed. And because we made this assumption about sort of proportional odds, or proportional hazards, this means that we're assuming that this hazard ratio is constant over time. So we are getting one number to represent the hazard ratio over time when comparing two cohorts. In the example I showed you earlier, we had different hazard ratios for each point in time, and now we've got one that sort of tries to summarize or represent the hazard ratio as a constant thing over time. And the whole finesse, so the whole reason you want to go to this length of calculations is because you could now add, well, we have one covariate here which represents if you've been exposed to something, a drug or smoking or whatever. But you could also add on covariates here for age and gender, socioeconomic status, etc., etc. The Cox proportional hazard has this word proportional in it, with an assumption that the hazard ratio is more or less the constant over time, or independent over time really. And you could illustrate it like this. If something is proportional, or if the hazard ratio is proportional, you'd expect to see two cohorts that sort of are proportional to each other when it comes to survival. So these are survival curves, and you can see they sort of have the same speed down, or the rate at which they differ stays the same over time. Is this proportional? Probably not. So if you're plotting the Kaplan-Meier curves and you get something like this, you might wonder if the proportional hazard ratio regression is the correct model. And in this case, it might be. But as I said when we started this part on survival, this is a very deep topic. I recommend that you get some help if you're not used to using or studying survival, but at least now you have a general idea of what it is about. There are a lot of different methods that you can use and different caveats that you should take into consideration. One step for you could be to read this statistical review on survival analysis. That could be one step forward for you, and there are a lot of other materials that you could also utilize.